Dear students, under the lecture series on graph theory, here we have lecture 15. The theorem says that a closed walk of odd length contains a cycle. Now, in order to prove this theorem, first of all, you should know what is a closed walk and what is a cycle and what is a closed walk of odd length. So, let us break these definitions now. We have already seen what is a walk, which is a sequence of vertices and edges. Now, a closed walk is a walk that starts and ends at the same vertex. So, if the initial vertex and the terminal vertex both are same, then it is said to be a closed walk. And what is a cycle? A cycle is a closed walk actually. It is same as this. The only difference being in a cycle, only the starting and ending vertex will be repeated and all the internal vertices will be distinct. Whereas in a walk that is closed walk, the starting and the ending vertex has to be compulsorily the same. And in between, we can have vertices repeated or non-repeated also. But in a cycle, compulsorily all the internal vertices should be distinct. They should not be repeated except the starting and the ending vertex. So that is the difference between the closed walk and a cycle. Now we know that the length of the walk is the number of edges in that walk. So now we are going to prove that the number of edges, that is a closed walk of odd length. So the number of edges in a closed walk, which is going to be odd, will contain a cycle. So this is what we are going to prove. So now let us prove this theorem by the method of induction. So we are going to prove this result by the method of induction on the length of the closed walk. So on the length, we are going to apply the method of induction and we are going to prove this. For that, first we should consider the closed walk. So what is the closed walk that we are going to consider? So let V0, V1, etc. up to Vn, where the initial vertex V0 and the terminal vertex Vn are chosen as generally V. And this is the closed walk of odd length that we are considering. So since we are applying the method of induction hypothesis, initially we have to start with n is equal to 3, because if n is equal to 1, it will be not an odd length of, it cannot be a cycle. So we are starting with n as 3. So a closed walk of length 3, and 3 is an odd length. So this is a closed walk of length 3. That is, it will be like this. So this is V1, V2, V3. We can, if we start the walk from here, V1 to V2, V2 to V3 and V3 to V1, because the initial and the terminal vertex are going to be the same. And we observe that it is a cycle. In fact, it is an odd cycle. So for if n is equal to 3, a closed walk of length 3 is a triangle. And since it is a cycle, we can represent it as C3. So hence the result is obvious in this case. So now after proving this, since we are doing the method of induction, we have to assume that the result is true for all closed walks of length lesser than n. So assuming this, now we have to prove that the result holds for closed walk of length n. So now in order to prove that, we are going to take a closed walk W. V0, V1, V2, etc. up to Vn, where the initial vertex and the terminal vertex are same. So this is a closed walk of odd length. Now if all the points, that is these vertices, these internal points, now all the internal points, if all are distinct and the starting and the ending point are alone same, in that case, the walk itself becomes a cycle, and therefore it contains a cycle which proves the required theorem. So we will write that. And the result is obvious in this case. So if all are distinct except the starting and ending, then the walk itself becomes a cycle of length n. And the result is obvious. So in this case it is done. Now we are going to take a case where all are not distinct. So in that case, we have to prove that it contains a cycle. So let us do that. So if they are not distinct, then there will be two vertices which will be equal to one another. So there exist two positive integers I and j such that I is lesser than j, and that will be not the initial and the terminal vertex. For that reason only we have put that I and j is not equal to 0 and n, not the initial and the terminal. So except that other internal vertices we are considering, and any two vertex will be same in that repeated. So in such a case, we are going to break this into two smaller closed walks. This one closed walk is going to be broken into two closed walks. So let us do that. So these are the two walks. That is, Vi is equal to Vj we have taken, which itself forms a cycle, and another walk is V0, V1, etc. Now Vi is equal to Vj, so we don't repeat it again. Then we start with Vj plus 1, etc. up to Vn. So this is the walk, and this is the cycle contained in this walk. So since this is a closed walk, so therefore we conclude that both W1 and W2 are closed walks contained in the given walk, and the sum of their length, when we add the sum of their length, it will be n. So therefore, since both W and W2 are closed walks contained in the given walk and the sum of their length is n, and since n is odd, at least one of these walks is of odd length. But we know that by induction hypothesis we have assumed that it contains a cycle for all with length lesser than n. So therefore by induction hypothesis it will contain a cycle. So hence we are done with the proof. So hence we have proved the required theorem. We can see an example, that is illustration for this now. So here we have a closed walk of odd length, because it just will be 1, 2, 3. Yeah, I have added one vertex. 1, 2, 3, 4, 5. So it is of odd length. And this will contain a cycle obviously. We can take the cycle as V1 and then V3, V4 and V1. So V1 to V3, V4 and then V1. So it contains a cycle. So I hope you have understood this theorem with the help of this illustration. Thank you.